depends on the magnitude of velocity squared. Well, that velocity has an x and y component. And what that means then is that my forces and my acceleration in the x direction will then depend on both the velocity in the x and the velocity in the y direction. Now, and this is in your book, by the way, we're not going to do any problems like this. And the only reason I bring this up is because I really like this problem. I've taught computational physics before, and this is one of the first ones we do when we're teaching computer simulation. Because it seems like something you should be able to do, but you really can't do this problem pen and paper. This is a good example of a problem that is just too hard to do using ordinary mathematical techniques and has to be done by finite differencing. And what I'm saying is the reason is because your forces and your acceleration in the x direction depends on a kinematic variable in the y direction, and vice versa. Your acceleration in the y direction depends on a kinematic variable in the x direction. And so those two equations are no longer effectively independent. And like I said, a problem like this, and they do show up, a lot of real problems. I mean, this is a real problem. Shooting a projectile at any real speed, like a bullet or a cannonball or anything, you can't ignore drag. And so the solutions we've been doing are overly simplistic, but the actual solution is more difficult than what we can do in this class. And a lot of real world problems are like that. We can simplify them, but at some point, those simplified answers might not be good enough. And so we have to address, how do we do this in real life? For example, we learned the range equation, that if we ignore air resistance, we know that the maximum range occurs at an angle of 45 degrees. And we have this nice picture here, and we can see that we get the same range at 60 degrees as we do at 30 degrees. We work this problem out in class. What happens if I add air resistance or drag? Well, it means the longer it's in the air, the more affected it's going to be. And so the solutions in the ideal case at higher angles are going to have a much shorter distance than they do in the ideal case. And you can see that. For reasonable assumptions about air resistance, it's actually the projectile aimed at 30 degrees, which goes further. It's in the air for a shorter amount of time, and therefore it's going to have less cumulative effect from the drag. And that allows it to have a longer range. And so the real world solution for this problem is that shooting the bullet at 30 degrees gives you a better range. Whereas in the ideal case, where you ignore drag, that's the wrong one, where you ignore drag, 45 degrees gives you a better result. And that's just the point of this, is that in a real two-dimensional system, these problems can get complex very quickly, but they're still interesting. Now, we aren't going to do any of these problems. I only bring that up because now we're going to spend the rest of the day talking about circular motion, which is two-dimensional. But we once again, in most of these cases, find a clever way to make it one-dimensional. The assumption we're going to make is that instead of talking about motion in the x direction or the y direction, we're going to be talking about motion as position along a circle. And if that's our variable, then, and we're going in a circle, we don't have to worry about the radius changing. All I have to do is worry about the angle changing. And so we've once again come up with a clever way of turning a two-dimensional problem into effectively a one-dimensional problem. Okay? So before we get started, I need to do a quick math review. This is stuff that was actually supposed to have been covered in chapter 4, but we skipped it. So, but I know you've all had pre-calculus and calculus, so this, I assume I can do this pretty quickly. What is a radian? A radian is the ratio of a section of a circle, we call that an arc length, to the radius of the circle. And it has the same attribute as angle. In fact, it is treated as angle in many cases. Angle in radians and angle in degrees can easily be converted because a full circle is 360 degrees, but a full circle has 2 pi times the radius, so a full circle is also 2 pi radians. Once you understand those two definitions, conversion between radians and degrees is fairly easy. The reason we're using radians for these problems is that whenever we're talking about position, There are certain equations that let us convert between angular variables like speed, like angular velocity, and linear variables like speed. And these conversion equations only work if you're using radians. And so these types of problems where we're talking about angular kinematics or motion in angular direction, we prefer to use radians for this type of a problem. Okay? Now, the technical definition then is that your angle in radians is the ratio of arc length s to radius r. I have a question for all of you, and I'm watching the chat. What are the actual physical units of radians? Do they have physical units? No, they don't, because it's the ratio between two lengths. And this one is interesting because it means radians don't have units. And we're going to see the consequences of that in some of the examples that we do coming up. Okay, but I'm glad you guys are cognizant of that. It means that you remember some of the theoretical work you did in previous classes. Okay.
Excuse me, Mr. Jones. I got a question for you real quick.
Sure.
I came in a little late. Do you want us to send our test corrections to your Canvas inbox?
Yes, just email them to me through Canvas. That would be the best way to do it right now. I do ask that if you have multiple pages that you combine them into a single file rather than sending me 6 separate files. But other than that, yes, that will be the best solution right now. And I'm going to see if I can set up a Dropbox to handle this more efficiently for the next exam. But for right now, yes, just email them to me.
Okay, thank you.
But by the end of the day. That's a great question. Okay. All right, so you remember this. You remember your unit circle. I hope everybody remembers at least talking about that. The 90 degrees is the equivalent of pi over 2 radians. 180 degrees is pi radians, and so forth. Do I need to say much more about radians? I'm assuming you guys are all good on this. Okay. So angular position, when we talk about the position of a rotating object, we usually use angle. The convention is that we start our angles from the positive x-axis, and counterclockwise rotation is considered positive. So if I'm rotating in the counterclockwise direction, my change in angle, delta theta, would be positive. Conversely, if I were rotating clockwise, delta theta would be considered negative. And remember, the change in angle is this is the actual angle. It is the ratio of my arc length to the radius of the circle. I can rearrange this equation and solve for arc length by taking arc length equal to radius times change in angle. And you've probably seen that before. Now, what happens if I have a spinning wheel, for example? Well, it's going from point A to point B, but it can't rotate from point A to point B instantly. It takes some amount of time. And so we can divide the change in angle by the change in time, and that would give us what we call angular velocity. Okay? Where's my picture? So let's say that I start out here at this position, theta 1. And again, remember, theta 1 is measured as an angle counterclockwise from the x-axis. If I rotate from theta 1 to position theta 2, which is right here, then my change in angle would be theta 2 minus theta 1. And that's how we've always done deltas. Delta means final minus initial. So here, my delta theta is the final angle, this one, minus the initial angle, and that gives me my change in angle. And that looks a lot like a kinematic equation for x, that delta x is equal to x final minus x initial. So in that sense, it's the same thing. Like I said, this change, this move from theta 2 to theta 1 takes time. If we take the ratio, or if we divide the change in angle by the change in time, that gives us a new property, which we call angular velocity. And that's represented by lowercase omega. It looks like a W. Often people call it a W. It's not a W. It's a curvy W, right? You've seen this before. Okay. So this is a lot like the definition we had for velocity in a linear system. Velocity is change in position over time. Omega which is angular velocity, is change in angular position over time, or rotation over time. Okay. Any rotating system like a wheel is going to be periodic, meaning if it goes around 2 pi radians or 360 degrees, you're back where you started. But we would still, if we were calculating delta theta, we wouldn't say delta theta was 0. We would say delta theta is 2 pi. So even though the wheel is physically back where it started, we know by the fact that delta theta is 2 pi that the wheel has gone through one complete rotation. And if delta theta were 6 pi, that would mean the wheel had gone through 3 complete rotations and so forth. And so we can use this value for theta, even if it's greater than 2 pi, and that lets us know how many times the object has made a complete rotation. Okay, and I already said this, but I'm going to say it multiple times because I find that this is something that catches students. Because it's a ratio of S over R, it is effectively unitless. Now, what does this mean? It means that sometimes I can just throw radians into an equation that weren't there before, and that might seem to be illegitimate, but it isn't because it doesn't have units. And so sometimes it appears and sometimes it disappears just because it needs to. And we can do that without actually changing the units of the problem because it doesn't have units to start with. Okay, so the next thing we want to talk about, let's say we have a disk or a wheel like the one I have drawn here. How fast are, linearly, talking about velocity, not angular velocity, how fast is an object moving if it's sitting on that wheel? Okay, or in other words, if I have a wheel like this pink wheel here, and I'm sitting at the very edge right here, and I'm going around with some angular velocity omega, what does that translate to in terms of actual speed? Okay, so this is important because we want to know this, especially if we're dealing with a car tire. What we can do then is we can say that this velocity here is actually the change in position, at least over a small segment. Okay? Remember that this delta S then is the same thing as r delta theta. We showed that on a previous slide. By the definition of theta being S over r, that means S is equal to r times theta. And so I can take my velocity at this point and rewrite it as r delta theta over delta t. Does everybody follow that argument? Well, as we defined on the previous slide, delta theta over delta t is the same thing as omega. And so what that tells me then is that my tangential velocity, and the t here, the little t here means tangential. It means velocity tangent to the circular motion. My tangential velocity then is equal to the product of r times omega. And this is an important result that we're going to be using throughout this chapter and some of the later ones. Now, this is the first example that I want to show you of how radians work. What should the literal units of our omega be? It should be meters times radians per second. Do you agree with that? What are the actual units of V? Come on, this is easy.
Second.
Okay, so what happened to the radian?
It just went away because it's not really, it's unitless.
That's a great way of putting it. It went away because we wanted it to, and we can get away with it because it didn't have units to start with. Now, it's not arbitrary as I'm making it sound. Whenever you multiply an angular variable by a distance, that's a good clue that the radian is going to go away. And we're going to see this again. But if you're ending up with funny units like extra radians where you know they don't belong, it's not wrong to just get rid of them. Because remember, they didn't have units in the first place. Okay, and I don't know if that's how it was explained to you in your previous classes, but that's how I like explaining it, and I find it useful to remind people that yes, the units do work out funny with radians, but you can always make them what they're supposed to be by just remembering that radians don't have units. Okay. So this is important because most of us have rolling objects that we use to get around places, whether it's a motorcycle or a car or anything else. What you're doing is you're transferring rotational motion of a disc, a tire, and using that to propel you forward. We've talked about this before. The fundamental assumption here is that the point of contact between the tire and the road is actually in static contact, meaning it's pushing on the road but not actually sliding. Well, the only way that could happen is if the forward motion of the car, I'm going to say this is the forward motion of the car, and the backwards motion of the tire at the bottom of the tire were exactly equal and opposite at this point, so that the actual speed of the linear speed of that point is zero. That's how come it's able to make a static contact. Well, in order for that to be the case, that means that the rotational speed of the tire has to be equal to the forward speed of the car. Now, why is this important? Most of you, unless you have a GPS-enabled speedometer, your car does not measure the actual speed of your car. What does it measure? It measures the amount of times your tires are spinning. And then by using the radius of the tire, it can convert that into a distance or a speed. So, like I said, if you have a GPS-enabled speedometer and it can tell you what direction you're going, then that's not the case. But for most cars, the speedometer is tied to the rotation rate of the wheels, assuming a certain radius of a tire, and that can be converted either into a distance or a speed using this angular conversion. All right? And you can show that by, if you were just to put your car up on blocks and run the accelerator, your tires would spin and your speedometer would say you were going 30 miles per hour, for example, but you would literally just be sitting there in your garage on blocks, right? Because it's measuring the rotation of the tires and assuming that the rotating tires are translating into a certain distance or speed based on this relationship. Do I have any car mechanic people here in the class? Yeah, until traction cuts off power. So if you're spinning your tires, then it's not going to be perfectly correct. Okay, Brian, tell me, what happens if you put bigger tires on the car? Do they have to adjust the odometer if you change the radius of the tires?
You do. Otherwise, you have to get a GPS to tell you how fast you actually are going.
That's right. And so if you, yeah, you can, I think, and again, you can tell me because I've been out of the country for 11 years, but my understanding is that if you lift or put bigger tires on these cars, that you actually do have to, it's like federally mandated that you have to reprogram the odometer and speedometer that it reflects the correct size of the tire. Is that mostly true?
Or you just change the tire size before you go in for safeties and emissions.
Oh, fair enough. That sounds a little bit duplicitous, but I can see that happening. Okay, well, good. So you understand the principle, though. Okay. Okay, I just got a message from the department coordinator addressing the question that was asked at the beginning of class. It says, yes, exam 2 will be through Proctorio, similar to last time. The test will be on October 5th and 6th, so that will be Monday and Tuesday of next week. Okay. Other than that, the test will be pretty much like it was before. If there are any additional changes, I will make sure you know about them as soon as possible. But the big picture is yes. Rather than the test being on Friday like we had it originally scheduled, it is moved to Monday and Tuesday. And I assume that will be true for all of the remaining tests as well. Okay, and the reason we did that is because there were a lot of people who just could not schedule and take the test on Friday. They had other obligations and things on their Fridays. So we had to make that adjustment.
Well, doesn't Slick try to schedule so Fridays doesn't have anything anyways?
And so people schedule like extra work hours on those days.
Yeah.
Which is what I was running into with multiple students. And I do have to admit this as well. I know I've mentioned before that this is my first semester, but at my previous school, everybody was a full-time student. And so a lot of this work-school balance is something that I'm learning to deal with because I know most of you work either part-time or full-time. And all of my students before that, I knew that they were full-time students. I could get away with pushing them a little bit harder. And I already know that I have to be careful with that in this class. But anyway, that's a tangent, an off-topic subject. So, continuing with this, and then we'll get into some examples. I hope you did see I put example slides up again. Uniform circular motion. Let's define that really quick. I'm going to do it later, but what do I mean by uniform circular motion? Circular motion is pretty obvious. It means you're going in a circle. What do I mean by uniform?
You're traveling at the same speed.
The same speed, but not the same velocity, and that's a great observation. So uniform means that yes, your speed and your angular velocity are constant. Now, there are a couple of ways we can describe this type of motion. We can either use the period, which is the amount of time it takes to make a complete cycle. We can use frequency, which is the inverse of period, meaning, for example, if it takes 5 seconds to make a complete rotation, then the frequency would be 1/5 of a rotation per second. And then finally, there's the one that we just introduced called angular velocity. That's what omega is. These three descriptions are related, and I'm going to tell you how they're related. First of all, I think the easiest one is period. If I took out a stopwatch, let's say I did have a spinning wheel, and I put a piece of orange tape on it, and I literally measured the time it took to go around once. That would be the definition of period. Period is usually represented by capital T, which I know we also use for tension. I'm hoping that it will be clear in the context of each problem what is being referred to, but yeah, we kind of run out of letters at some point. Okay, does everybody understand what I mean by period? And this applies to things other than rotating systems. It applies to any type of periodic motion. Okay, frequency is literally the inverse of period. It's an easy calculation. If I can calculate the period, 1 over period is frequency, and conversely, period is 1 over frequency. And it is the number of times per second that an event occurs. In this case, it would be the number of times per second that the object rotates. The units we use for period are seconds. The units we use for frequency are inverse seconds, which are called hertz. And you see this on your computers. One of the metrics for how good a computer is its processor speed. Processor speed is usually measured in gigahertz. Giga means billions of cycles per second. Right? A megahertz is 1,000,000 cycles per second. A gigahertz would be 1,000,000,000 cycles per second. So if you have a 2 gigahertz processor, and I know everyone has multiple cores and everything, but if we just had a single 2 gigahertz processor, that means it's going through 2 billion computational cycles per second, which is really quite amazing if you think about it. Okay, the final one is angular velocity. Angular velocity, as we said before, is represented by the Greek character omega, and it is the number of radians per second that the angle is traversing. Now, omega and frequency are related because one complete revolution is 2 pi radians. So if I take my definition of frequency, frequency is the number of revolutions per second. If I replace the revolutions per second by radians, then I have to include that 2 pi there. So omega is equal to 2 pi times my frequency. And again, the 2 pi comes from converting from a complete cycle into radians. There's 2 pi radians in a complete cycle, a complete rotation. Okay, so if I were to give you a wheel, for example, and say that it makes that it makes 5 rotations per second. All right, so let's say I give you your frequency. I say my frequency is equal to 5 hertz. That means it's making 5 complete rotations every second. Does everybody agree with that? Okay. Each rotation is equal to 2 pi radians. So I could multiply that by 2 pi radians. That converts rotations into radians. And that would be equal to 10 pi radians. And in this case, I would take my hertz and I would convert that into 1/seconds, and I would say something like this. So you all see how that conversion works, right? There's another commonly used unit for rotation, and that is RPM. What does RPM stand for?
Rotations per minute.
Rotations per minute or revolutions per minute, and they're both correct. I mean, because they both kind of mean the same thing. So how would I convert this? If I were given my angular velocity in RPM, how would I convert that into radians per second? I'm going to say revolutions per minute. Well, how would I convert what's the conversion between revolutions and radians? 1 revolution is the equivalent of 2 pi radians. Do we agree with that? One complete revolution is the equivalent of 2 pi radians. Okay, the next conversion is minutes to seconds, and this one's easy. 1 minute is the equivalent of 60 seconds. So if I do this, let's see, minutes cancel with minutes, revolutions cancel with revolutions. What I'm left with is a conversion of 2 pi radians over 60 seconds, or pi over 30 radians per second. And that's how I convert between RPM and radians per second, is I would take my value in RPM and I would multiply it by pi over 30. That would give me my answer in radians per second. And we could do the opposite if I needed to go from radians per second into RPM. The reason I bring this up is some of the problems on your homework are in radians per second. Some of the problems are in RPM. And so it's helpful to know that you can easily convert between those two sets of units. Okay, are there any questions? Okay. So we were talking about uniform circular motion. Here's a couple of things that we expect from uniform circular motion, and some of this we already talked about in chapter 4, but we're going to talk about it again because, again, based on some of the discussions we were having at the beginning of class, I still don't think this is getting through. The magnitude of the acceleration needed to keep an object in circular motion is called centripetal acceleration. And the equation for centripetal acceleration, we call it AR. The R in this case means acceleration in the direction of the radius. So we can also call this radial acceleration, but today I'm going to call it centripetal acceleration. And I'm not going to prove this equation, but it can be shown using geometry, that acceleration is equal to v squared over r. And when I say v, I mean the tangential speed, the speed of an object as it's going around the circle. So radial acceleration or centripetal acceleration is equal to v squared over r. Like we showed on a previous slide, v is equal to r omega. if I replace that into here, what happens? I get r squared omega squared divided by r. One of the r's cancel, and I'm left with the second representation that centripetal acceleration can also be written as r times omega squared. Does everybody see why that is? If I were to substitute this definition into the equation I have circled, I would get the final equation, or the final representation. Okay, so both of these, depending on your question, if your question is dealing with velocity, you would use this form. If your question is dealing with angular velocity, it would be easier to use this form. And just remember that there are two different ways of calculating centripetal acceleration depending on the nature of the problem or the information that you're given. Okay, now here's the part that's probably going to be trickiest, and so I'm going to take some time on it. Whenever there's an acceleration, we know there must be a force. Do we all agree about that? What is the force that causes centripetal acceleration? We call it centripetal force, but that is a little bit misleading because there is no such thing as centripetal force. There are, however, forces that cause centripetal acceleration, and we sometimes call those centripetal force. I'm going to make a big deal of this in a minute, but I want to point out centripetal force is always caused by other forces like tension or gravity. Centripetal force is not a force itself. It is the result of other forces. And if that doesn't make sense now, give me a few minutes and it hopefully will. However, the principle of this is pretty easy. F equals ma. So if I know that this is my acceleration, then I know that this is my force. It's just whatever my acceleration is times mass. So when we talk about centripetal force, this is the definition of centripetal force. I just want to emphasize to you from a conceptual point of view that centripetal force isn't an actual force that you would draw on a diagram. Okay? And we're going to do some examples that I hope help that make better sense. But if we talk about if a problem asks you to calculate centripetal force, it's asking you to calculate centripetal force using either of these two methods, depending on the information that you're given. Okay. Another thing I want to point out before we go into examples is that both of these equations have tangential velocity in them, and often that won't be given to you in the problem. Well, there are ways of finding tangential velocity using other methods. Either we can calculate omega, or we can use, if we're given period or frequency, we can use the circumference of a circle. We know the circumference of a circle is 2 pi r, and we can say that the tangential velocity is the distance it travels, that's the circumference of a circle, divided by the time it takes to make one complete circle, and that means that my tangential velocity is equal to 2 pi r over t. Now, if you're paying attention, you'll realize that using this definition for v gives you back mr omega squared, because omega is 2 pi over t. So again, these two equations are saying the same thing. This is another way of conceptualizing that idea, that if you're given a problem and you don't know what the tangential velocity is, you can calculate it if you know what the period or the frequency of the rotation is. Okay, how are we doing? Okay, back in chapter 4, I did a few exercises with you. I'm going to try this again. We'll do that in the next slide. Okay, a few things I want to say about centripetal force. First thing, centripetal force is in what direction? Always towards the center of the circle, always. And I just made a big deal that centripetal force isn't a force, but as you're going to see, it tells us what the net force is. So centripetal force, if an object is going in a circle, we know that the net force has to be towards the center of the circle. That's what those red arrows on the picture represent. Because the net force is towards the center, that means acceleration is always towards the center. Now, this one is the thing I was trying to make a big deal of on the previous slide. Centripetal force is always caused by other forces and is not an actual force itself. In fact, you know what? I'm just going to skip to the next slide because I want to, and we'll come back to this. Here I have a car going around a turn. What force is keeping the car from sliding off the road?
The friction from the tires?
The static friction from the tires. Good. So, and what direction would that force be? It would be towards the center of the circle. What would happen if there weren't a force towards the center of the circle? The car, instead of going in a circle, would go in a straight line. Just like if you try taking a fast turn on an icy road, you don't have friction and you don't make a turn, you just keep going in a straight line, just like Newton's first law says you should. Okay? So what I want to emphasize here is, yes, there is a centripetal force pointing towards the center of the circle, but it's not centripetal force itself, it's the force of friction causing that centripetal acceleration. Okay, the actual force here is friction. That's what I really want to get to. Okay, we have a person hanging on a merry-go-round going around in a circle, and that means there is a force pulling her towards the center. What is the actual force that allows her to stay on the merry-go-round?
Her grip strength?
Yeah, and I'm going to call that a contact force. It's not exactly the same as normal force, but it's the fact that she's holding on, her pulling on the merry-go-round, she's pulling herself towards the center. And so it's the force of her pulling on that bar that provides centripetal force. Okay, so I'm just saying every time you see circular motion, there's an actual force causing that motion. It's not a mysterious centripetal force, it's an actual physical force that you can identify. Here we have, this one's trickier, but we're going to do some problems like this. Here we have a car going over a hilltop. What direction is the centripetal force? We talked about this before.
Down?
Down because it's towards the center. What is causing that centripetal force?
The
This
weight
time
of the
it's actually
car? Gravity?
the weight of the car, but there's two forces acting in the y direction. So I can say that there's gravity pulling down, mg, but there's also a normal force pushing up. What does that infer? And I drew it the right way this time. If I know that my net force is downwards, what does that tell me about the relationship between my normal force and my gravitational force?
That the gravitational force is bigger?
Yeah. And so in this case, my centripetal force would actually be equal to mg minus n. Okay, so in this case, here's what I'm trying to tell you. In this case, it's not a single force, it's the combined effect of two forces that give me centripetal force. Okay, how about this one? Earth going around the sun. What is the force that keeps the Earth in its orbit around the sun?
Gravitational pull from the sun.
It's gravitational pull directed towards the center of the circle, directed towards the sun. And in this case, it's a single force, but once again, it's not a mysterious centripetal force that keeps the Earth in orbit. It's gravity that I would say it's more appropriate to say that the centripetal force is provided by the force of gravity. Do you understand the distinction I'm trying to make here? There is no situation, and I want to stress this, where you would ever draw centripetal force as an actual force acting on an object. It's always some actual physical force that we've already talked about acting on the object that provides that force. Okay, so hopefully with these examples in mind, what I'm going to say next makes better sense. Okay, centripetal force is not an actual force, but is the result of other forces. Does that make, I'm hoping that makes sense, if nothing else. Okay, here's the next one. Centripetal force is not something you would draw on a free body diagram because it's not an actual force. You would draw the actual forces acting on the object and say these forces, like, for example, normal force and gravitational force, these are the forces you would include in the free body diagram, and they are the ones that you recognize are causing the centripetal motion, but you would never draw an arrow and call that centripetal force. And I'm telling you that, and I'm hoping that your author doesn't do anything like that and make me look silly. Because I admit I haven't had time to read the entire book yet, but I'm pretty sure that he agrees with me on this point. And if he doesn't, then I'll look silly later on. But this is the way I'm teaching it. Centripetal force is not a force. It doesn't show up on a free body diagram. And it does not show up on the left side of Newton's second law. What do I mean by that? Newton's second law is net force equals mass times acceleration. Centripetal force would never show up when you're adding forces together. The things that show up on the left side of this equation here are actual forces. For example, gravity, normal force, tension, whatever, and friction. The real forces are the things that go in here. Okay? Where does centripetal force show up? It shows up on the right side. It would show up here. Now, why do I say that? Well, if an object is going in a circle, I know what its acceleration has to be. The fact that it's going in circular motion means that I know that this acceleration on the right side of Newton's second law must be v squared over r. So the result of all those other forces is that I end up with centripetal force on the right side. It's the result of all the other forces. So centripetal force, if you want to think of it, will show up as the result of all the other forces. That's what we get on the F equals ma, on the mass times acceleration side. That's where you see centripetal force. It's the result of the other forces. How do I know? Well, if it's in a circle, I know that the acceleration has to be v squared over r. Otherwise, it wouldn't be in a circle. It would be something else. Okay, how are we doing? Okay. I even wrote that there. I forgot I had that in there in the slide. Okay, so real forces go in here, and as a result of adding up all those real forces, you get centripetal force as a result. Maybe that made better sense when I said it that way. Are there any questions? Okay. So let's do one more example. Let's say I have a ball, I tie it on a string, and I'm spinning it over my head like this. Okay. And I give you what the mass of the ball is, I give you the radius of the string, and the frequency. We'll deal with those later. What is the actual force that keeps this ball in circular motion? And I'm cheating a little bit because it's drawn on the picture, but there's an actual physical force that we can identify that's keeping this ball from flying off into space. It's tension in the string. If I let go of the string, it would not go in a circle. It would go off. Well, we'll talk about that in a minute, but we can agree that it's the tension in the string that's providing centripetal force. Right? Now, the next thing, because this problem is a lot like problem 4 on the last exam, the ball is in motion. It's clearly in motion. It's going around from our perspective in a counterclockwise direction. What direction is the net force or the centripetal force? It's towards the center of the circle. Okay, so if I said center of the circle, that would be an answer. If I actually drew a picture here, I would say that the net force is acting in this direction. Now, if I gave you the option of saying, what direction is that arrow pointing? Is it pointing to the left or is it pointing to the right?
To the right.
Okay, and I don't know, I mean, again, I don't know why that question was quite so hard, but that's really what it meant when it said, when option 1 on question 4 of the last exam said that the force or the acceleration of the object was to the right, it literally meant that because the thing is over here and the force is pointing towards the center, that the force vector is pointing towards the right, meaning your right, like your right hand. And I know that my picture gets reversed, but if you were to say the left side of the page or the right, maybe that's how the problem should have been worded. Is the force towards the left side of the page or the right side of the page? If it were worded that way, I think people would have done better. I think what happened is a lot of people thought it was either spinning or rotating in a right-handed direction or a left-handed direction, and that's how that problem got misconstrued. But this is what it meant to ask. It says, recognize that the force acting on the ball is towards the center, and the way the picture is drawn, towards the center means pointing to the right. Okay, so I hope we don't have to do that again. Now, the reason I say estimate here is because this isn't purely horizontal. There's a small amount of dip here, but we're going to say it's small and ignore it. If we just take the information we're given, how would we find the tension in the string? The first thing I want to do here is to find the tangential velocity, vt, because I'm going to need that. What is my tangential velocity?
It's the radius times omega squared.
Radius times omega squared. That would be my radial acceleration. I agree. Okay, so you're a little bit ahead of me. AR would be equal to R times omega squared. That's not what I'm asking, but that's my next question. So you're just ahead of me. Okay, let's back up a second. What if I wanted to find the actual tangential velocity? What if I wanted to find the velocity? I'm going to draw it right here and call it tangential velocity. Meaning how fast is the ball actually? Yeah, I would say, so what I would do here is I would say it's equal to R times omega. But we're not given omega, are we? So I'm going to use this one instead. I'm going to say it's R times 2 pi over t, because that's one of the ways I taught you to calculate tangential velocity. It's equal to the circumference of the circle divided by the time it takes to make a complete cycle. Well, we're not given period either. We're given frequency. So I'm going to replace the t here with the 1 over t here with f. And that's not friction, that's frequency. Does everybody understand how I got this equation? And yes, you guys are, Christian, I agree. You guys are thinking about this a correct way, just a different way than what I'm doing. You could also say omega is equal to 2 pi times f, and then you could solve this equation. So if you guys want to do it this way, go ahead. I'm going to do it a different way. We can check and make sure we get the same answer. I'm going to say Vt is equal to R times 2 pi times f, and I get that my tangential velocity for this is equal to 7.54 meters per second. Okay. Now I can write my Newton's second law. I'm going to say net force acting in the R direction, I could use x if I wanted to, is equal to the force of tension in the x direction. That's the actual force, right? And that's equal to my mass times my acceleration. Okay. Well, what are we solving for? We're solving for tension, so that's good. So that means Tx is equal to mass. What's my acceleration? In the r direction, it's going to be v squared over r. How come I could get away with doing that? It's because it's going in a circle. If I know that the problem is going in a circle, then I know that the acceleration I have here is v squared over r. And so then that gives me my tension is equal to 0.15 kilograms. We just calculated V. This is why I wanted to calculate V times 7.54 squared over R, which is 0.6. And I get 14 newtons. 14.2 newtons. Okay? Now, I could have done the same thing, and I think this is what a lot of you were trying to do. Instead of using V squared over R here, I could have used R omega squared, and then I would just have to, instead of calculating V, I would have calculated omega. Using, like Christian said, R times say R, they would actually be, my omega would be equal to 2 pi times frequency, but the idea is, yes, you could do this by solving for omega and then using that for your centripetal acceleration. I chose to solve for V and then use V squared over R. You'll get the same answer both ways. Okay, are there any questions about how I did this problem? I propose that we take an 8-minute break at this point. It's 9:02 on my clock. Let's take a break and come back at 9:10 and we'll do more examples. Okay? All right. So I'm back. And guys, I need to apologize. I realized that I forgot to turn on the record for the first half of the lecture, and I am sorry for that. If any of you, I know it's not your job, but if any of you want to remind me when I forget to hit the record button, if you could gently remind me to do that, I would actually really appreciate that. And it would probably help the students who aren't here today. Although I'm looking at my chat thing and it looks like everyone's here today, which is really good. But yeah, and I don't know if you're using the recordings, but just remind me to hit record and then this button turns red. You can all see that that button just turned red, the record button. If I forget to do that, please just remind me. And again, that's not your job. You're students, I'm the teacher, I should be doing this, but you know, I'm not perfect, and this is one thing that I obviously messed up on today. Okay. Yep. So that's what I'm saying. We can make this a team effort. Okay. So yeah, I'm missing the first half, and I'm sorry about that, Nadia. That wasn't intentional, but if you have questions, I'll do my best to try to explain them. Okay, moving on. I have a question for you guys. This is related to the problem we were just doing. Yeah, I will record my next one, and I think I can send you guys the link for my second class. I should be able to do that. That's not a bad idea. Okay. So let's say that I'm spinning this ball over my head like this, and I do decide to let go. Which of these two scenarios makes better sense? That the ball will accelerate outwards, or that the ball will accelerate tangent, or back up. Which of these two scenarios makes better sense? When I release the ball, that it follows the path shown in picture 1, or that it follows the path shown in picture 2?
Picture 1.
Okay. And what I want to stress here is there's not a force pushing it outwards. And this is a misconception. There's no centripetal force pushing outward on the ball. If there were, you would expect picture number 2, right? What there really is just the inertia or the motion of the ball carrying it forward. As soon as you stop accelerating it, instead of going in a circle, it goes in a straight line, according to Newton's first law. And that's picture number 1, and I agree with you. The misconception or the false idea of centripetal force often leads people to think of scenario 2, that there's some force physically pulling the ball out from the circle. When in reality, it's that there's a force pulling the ball in the circle while it's kept in the circle. That's our centripetal force, which in this case is really just tension. Okay? And so while this seems like a very obvious question, I want to stress to you that there is no centrifugal force pushing the ball outward. All it's doing is going in a straight line. Okay? But if you hear discussion of centrifugal force, that is not a physically correct force when you're dealing with inertial reference frames. Okay, let's do another example. I have a car driving over a rounded hilltop. Oh, you know what? I already did this problem. Anyway, I'll ask it and just see if you guys remember what we talked about a half hour ago. I have a car traveling over this hilltop. What direction is the car accelerating?
Negative y.
Yeah, it would be this one right here. And how do we know it's negative y? Well, if it wasn't, it would go in a straight line like this, and it would basically hop off the hilltop. And if you go fast enough, that can happen. Maybe some of you have actually tried doing that on dirt roads or something before, taking the bumps fast enough that you catch a little bit of air. But for normal driving, you don't want that to happen. All right? And so that means there has to be some force causing your velocity to follow the contour of the curve. And that means there has to be a downward acceleration. We already talked about where that comes from. It comes from the balance between gravity pulling down and normal force pushing up. So I just get a second opportunity to discuss this problem again, which is good because these are problems that you're going to see on this homework. Okay, let's do another example. Car in a curve. Let's say we have a car with a mass of 1,000 kilograms, and it's going on a flat road, meaning it's not angled, it's not inclined. It has a speed of 10 meters per second, so it's traveling at a constant speed, and a radius of the turn is 50 meters, and it's going through the turn. We've already talked about this. What provides the force that allows the car to make this turn? What actually is the source of this centripetal force?
Friction.
Yep. And more importantly, static friction. Again, this is assuming that you're driving under normal conditions. And in both this class and the other class, we've pointed out that yes, you can slide through these turns and then it's kinetic friction. And I'm really hoping no one drives that way in a real sense, right? No, none of you drift or whatever that is. You all drive like normal, sane people. Okay, so that, assuming that you drive like a normal, sane person, the force that provides this turning friction, or this turning force, is static friction, acting again towards the center of the circle, like you would expect. Now, that makes drawing a diagram or a free body diagram for this a little bit tricky, but here's one way of thinking of it. Let's imagine the car if we were looking from the back of the car. What would be the forces acting on the car? There are three of them.
Well, you have them drawn right there, but it'd be the force of gravity, the normal force, and static friction.
Yeah. So the regular things I have force of gravity pulling down. That's what the W is. Normal force pushing up. Equal and opposite because of which law?
First law.
First law. Good job. So first law. Now, the static friction is going to be perpendicular to the surface. And we knew that was going to happen already, but it's not in the direction of motion. It's in the direction that would oppose this car. If it were to start to slide, it would slide out of the turn. And so there's a force of friction is keeping it pointing towards into the turn. And so this force of friction opposes the car from sliding off the road. That's how you can think of it in terms of friction opposing motion. And yes, it should be static friction under normal conditions. So now that we've gone through the conceptual part of this, how would we do the actual solution? Or in other words, what is the minimum value of mu that would keep the car from sliding under the conditions laid out in the earlier part of the problem? Okay, what I want to do is I want to write an equation for Newton's second law that would describe the forces acting on this car in the x direction. And that's why the free body diagram is helpful, because now we know what those are. I would say my net force acting, instead of the x direction, I'm going to call it the r direction, because that's what your book does. He uses r for radial and t for tangential. Let's try that again. The net force acting in the radial, meaning the r direction, is equal to, well, there's only one of them, and that's Fs. We already talked about that's our force of static friction. And that's going to be equal to mass times my radial acceleration. Well, that equation is correct, but it doesn't look very helpful yet. So we need to expand it a little bit. But this is my equation. Now, what do I want to use for Fs? What's the actual force of static friction for a problem like this? What's the equation we learned for force of static friction? Okay, the maximum force of static friction is going to be equal to mu s times my normal force, which is, in this case, mg. We can see that from our diagram. Now, this isn't necessarily the actual force, but it's the biggest, it's the maximum limit that the static friction could be. All right, so I'm going to use this in the equation because that will allow me to calculate what the minimum value of mu is. Minimum value of mu is when I'm going to be right at the limit of sliding, where I'm just at the point where I'm about to slide. So I want to use this full version of mu times normal force. And that's going to be equal to mass. Now, because it is going in a circle, the problem says that it's going in a circle, that means I know what this value AR is, or at least I know an equation for it. It's going to be equal to V squared over R. And so again, like I said, the centripetal force always shows up on the right side of the equation, and real forces always show up on the left side of the equation. Is that making better sense now? Because I can't see your faces except for one of you, and so I can't really tell whether I have such a hard time knowing whether you guys understand what I'm talking about. But is this making better sense, what I was trying to talk about before? Real forces go on the side where we're adding forces. Centripetal force goes on the... Okay, let me make sure I say this right. Real forces go on the left side. That's where we're doing net force. Centripetal force shows up as a result on the right side where we're doing mass times acceleration. Is that making better sense now?
I think the way that it seems to make sense to me is just to think of the centripetal force as all the forces that are creating, that are causing acceleration towards the center of the circle, like that are along the radius. And so if you just figure out what those forces are, those are like your net forces that are causing the centripetal force. So those go on the left. You just identify what those forces are. In this case, it's just static friction. And then on the right, it's just as normal. You have mass times acceleration. And we can consider acceleration to equal velocity squared over r, or
because it's going in a circle. That's exactly right. That's a great explanation. Okay, so now that we've got that, we can solve this equation for mu, can't we? Because we have everything else. In fact, I didn't even need to give you mass, because in this case, mass cancels from the left and the right side of the equation. And so what I'm left with is that mu is equal to V squared over G times R. Okay, I run that through my calculator using the values that are given in the problem, and I get 0.20, and it doesn't have units. And that's something you should check. We expect mu not to have units. The term in the denominator is going to be meters squared over seconds squared. The term in the numerator is also meters squared over seconds squared. And so the units on the top and the bottom cancel out, and we're left with a unitless number. And is this reasonable? I know I told you not to memorize that table of friction coefficients, but under normal conditions, you would expect to have a coefficient of static friction of between 0.8 and 1 for a car on a road. So 0.2 is far below that, and so that means that this is a very safe turn. You're nowhere near the maximum limit of friction, right? Having 0.2 means you could probably make this turn even under wet or icy conditions. You would still have enough friction to be able to do this turn. Okay. How are we doing? Do you guys have any questions before we go on to our next examples? Okay. So let's talk about non-uniform motion. Is it possible to be going in a circle and changing speed at the same time? Yeah, that's what happens for example, to your tires on your car when you're actually accelerating. If you're changing speed, the tires are spinning, and they're also spinning either faster or slower depending on whether you're accelerating or braking. So that would be considered non-uniform circular motion. It's still circular motion, but it's not at constant speed. Now, this is obviously going to be more difficult, and it introduces a second type of acceleration. You still have radial acceleration, but now you also have tangential acceleration, meaning acceleration in the direction of the rotation of the tire. Okay? Now, we're not prepared to deal with that just yet. I'm introducing it. We will deal with this in more detail, but I'm just curious, what causes tangential acceleration? Or in other words, what would cause a rotating object to speed up or slow down? Does anyone know the concept for that? And if you don't, it's fine because we haven't introduced it yet. A shorter radius, that would be, that's not what I was thinking, but you are correct. No, I was thinking if I actually had a wheel and I wanted to make it spin faster, let's just say I had a bike wheel just sitting here and I wanted to make it spin faster, what would I have to do to it?
Apply more force.
Apply more force, and there's a special name we have for force acting on a rotating object.
Torque.
Torque. Now, again, we haven't gotten to that yet, but it's coming up. Anytime you have tangential acceleration, it's because, like you said, there's a force acting tangent to the circle, which is equivalent to a torque. All right? And that just gives you a little bit of a warm-up for what's happening. So radial acceleration is just the same as it was before. It's equal to whatever the instantaneous or velocity is at that point in time, squared divided by r. The tangential acceleration, we're not ready to deal with yet, but I'm just kind of giving you a teaser going forward. Tangential acceleration requires some external force applying a torque to the system. Now, the nice thing is that radial acceleration is always going to be perpendicular to tangential acceleration. I know the notation in this picture is slightly different, but I think you can understand that the A tan is the same thing as AT, and the big R, little r, it's whatever. The nice thing about this is if I needed to know the net acceleration at this point, I can just add those two vectors as perpendicular components of a new vector using Pythagorean theorem and using inverse tangent. And we've done this a lot, so and there aren't any problems like this on this homework, but there will be on some coming up. I'm saying if I can calculate what my tangential acceleration is and what my radial acceleration is, I could find the net acceleration and the net force. And this time it's not exactly pointing towards the center of the circle, right? The radial acceleration still points towards the center of the circle, but because now there's also a tangential component, it means that for non-uniform circular motion, the net force won't necessarily be pointing at the center of the circle, but its radial component obviously will. Okay? And so I could find the magnitude of that acceleration by just using Pythagorean theorem, and I mean, that's, I'm hoping, fairly straightforward. And we'll deal with this problem on another day. But what I want to do is we're going to do some problems where we don't actually calculate that tangential component of acceleration, but we consider its effect. All right? And I'm going to do this because there are several problems on your homework similar to what we're going to do next. And that is to say, let's say instead of, you remember I was spinning the mass around my head like this in a horizontal circle. Well, I could also spin it around in front of me like a shield. And then it would be a vertical circle. You guys can imagine that, right? Here's the thing. If it were a solid wheel, it would be uniform motion, like a Ferris wheel or an actual wheel. Because it's a solid, all the points have to rotate at the same rate because it's a solid. But if it's a mass on a string, what do we expect to happen? As it goes up, we expect it to slow down, and as it goes down, we expect it to speed up. And what that means is that the actual velocity, the tangential velocity here at the bottom, will be greater than the tangential velocity at the top. And so this is an example of non-uniform circular motion. And without going into all the details, the reason it's non-uniform is because of the effect of gravity causing it to slow down as it goes upwards and speed up as it comes downwards. Okay, rather than trying to deal with that directly, let's ask two questions. When it's at its highest point right here, what forces are causing centripetal acceleration? And I know they're drawn on the diagram, but what are they?
Gravity and tension.
Which are pointing in this case in the same direction, towards the center of the circle. Okay, and then just thinking ahead, what are the forces at the bottom that are causing centripetal acceleration?
It's the same, they're just in different directions.
Great, that's exactly what I wanted you to observe. That we still have tension and gravity, but in the top case, gravity is assisting tension by providing some of the centripetal force. In the bottom case, gravity is working against tension, meaning tension has to be even larger. Tension has to provide both the centripetal force and it has to provide the support against gravity. So that means you expect the tension at the bottom to be a lot larger than the tension at the top. Okay, and again, I'm going through the conceptual part of this before we do the throw equations at it. If you were doing this, where would you expect the string to break? If you were to spin it too fast, where would you actually expect it to break?
At the bottom.
At the bottom, because that's when it's experiencing the greatest stress. Okay, so how would I actually calculate the tension? I'm not going to give you numbers, but let's say that I actually wanted to calculate this value Ft at this point up at the top. How would I go about doing that?
You would add up those forces and set it equal to the mass times the x.
Okay. And you have to be a little bit careful here. For this one, I'm gonna pick a coordinate system where down is positive, and that way all my forces are positive. I don't have to do that, but it makes things so much easier. If I pick the other one, then all my forces will be negative. So I'm just gonna say that down is positive for this part of the problem. And that means then, just like was pointed out, that the net force acting in the r direction is going to be equal to, you know what, that's even better. And instead of calling that y, I'm going to call it r, and then it's obviously positive in that direction. And that would be even better because that's consistent with how your book does it. The net forces acting in the r direction are going to be equal to mg plus my force of tension. I'm going to use your book's notation, T. And that's going to be equal to mv squared over r. Now, that means that if I knew what v is, if I were given v, I could solve this equation for t, and that would give me then that t is equal to mv squared over r minus mg. Well, what is this telling me? It's telling me that tension is providing some of the centripetal force, but if I subtract out the effect of gravity, that means tension isn't as big as it would normally be, as it would otherwise be, because gravity is providing some of that downward force. Now, is there any situation? First of all, does everybody understand how I got this equation?
Can you go over how you went from mg plus t to m times v squared over r?
Okay. Newton's, yes, I'll do that in more. There we go. My eraser's acting funny. What are the two forces acting in the r direction for the top? If I'm defining r to be this down arrow, what are the two forces acting in the downward direction on ball 1? If I'm going to add up those forces, what are they?
Gravity and the tension.
Okay, so that's just the net force acting in the r direction. Newton's second law says that the net force acting in the r direction is going to be equal to mass times acceleration in the r direction. Does that make sense?
Yeah, I see now.
Okay, what is acceleration in the r direction? Well, because it's going in a circle, we know that that acceleration in the r direction must be v squared over r. Now, I can solve this, like I said, for tension, and that would give me tension is equal to mv squared over r minus mg. Now, is there any physical situation where tension could be negative? Would it make sense for the tension in the string to be negative? No, it wouldn't. That's not how strings work. What it would mean is if the tension in the string were negative, that we no longer had tension in the string. Once it reaches 0, then the string goes limp, right? And that would mean if I were actually spinning the ball in a circle, if I reached a solution where t was negative, it means that it would no longer have enough force to keep it in a circle, and it would basically just fall down. You can imagine that. If I were to spin that ball like this, if I were to spin it too slowly, what would happen as it goes through the top motion? It would fall out of that circular path, right? And that's what I'm saying. The physical condition that would describe what I just said would be a solution. Any solution to this equation that came out with t being negative is effectively saying the same thing. You just lost tension in the string. It's no longer going in a circle. There are a couple of questions on your homework that are similarly phrased, and it's just saying, when does the object fall, or when does it no longer, when does it jump off a curve or whatever? It's when you come up with some equation like this that leads to a physically impossible situation, like t being negative. That's an indication that you no longer have the conditions for circular motion. Which leads to my question down here, we'll deal with in a minute. Okay, but I want to stress to you, having tension being negative doesn't make sense. So that means that there always has to be a little bit of tension in the string, otherwise it wouldn't be going in a circular path. Okay, so let's try the next one. What would be the tension at point 2 when it's at the bottom of its motion? Whoops. Well, I'm going to do the same thing, except now I'm going to be using a coordinate system where r is in the positive direction. You know what? I don't like that color. Let's try a different one. Okay. Because r now is pointing up, when I write my equations, I'm going to be using up as positive. So that means that for my second one, net force in the r direction is going to be equal to t in the positive direction minus mg, because it's in the negative direction in this new coordinate system. And that's going to be equal to mv squared over r, like it was before. But the important thing here is to recognize that now mg is working against me instead of with me, which is what we conceptually described when we were going through the concept of the problem. As a result, t now is equal to mv squared over r plus mg. And that means that the tension of the string is going to be the necessary force required to keep the circular motion. And in addition, it's going to be equal to the weight of the string. And it's even worse than that, because as we said before, we expect v in this case to be larger than it was at the top. So all of that combined means that your tension at the bottom is going to be considerably larger than your tension at the top. Okay, now as a result of these two conclusions, or at least the first one, what is the minimum tangential speed? Meaning, what is the minimum value of v here that would allow me to keep circular motion? Well, remember I said we can't have negative tension, right? So I'm going to say that in order for tension not to be negative, that this term here on the left, mv squared minus mg, has to be greater than or equal to 0. Which is the same as saying that mv squared over r must be greater than, I'm just going to get rid of the equal, must be greater than mg. Does everybody, this is the condition that would keep t from being negative or 0. Does everybody agree with that? Going from this equation, if I'm saying that t cannot be 0 and cannot be negative, that means that this term, mv squared over r, must be bigger than this term, mg. Which is then equivalent to saying that v squared must be greater than gr. And then I could take the square root of both sides, ignoring the negative solution. That would just tell me then that v must be greater than the square root of gr in order for my tension to remain positive. And if my value of V were to fall below that, that's when I would expect to lose tension in the string as it goes through its upwards motion. And then it wouldn't be in a circle anymore. Okay. Good. I actually timed this one correctly. I have one more example and then we'll be finished for the day. And we can talk about a few things about the test and some other stuff. Are there any questions before I go on to my final example for the day? Okay. So, in Winter Olympics, they have a sport called bobsled, where they're going through an icy track at high speed. And some of you might even remember, I think it was about 6 years ago, there was a defect in the track, and they had an accident while they were training for the Winter Olympics, and several of the bobsledders were severely injured. And I know that was a while ago, but does anybody remember that instance? They actually had to rebuild most of the track, make it slower. Okay, well, here's the idea. You have these bobsledders, they're coming through this icy ditch, this tube, and they have to lean to make this turn, and the turns can be at different radii. I'm going to say that they're going at constant speed, so that the speed in both turns is 34 meters per second, but the first turn has a radius of 33 meters, the second turn has a radius of 24 meters, and before we calculate this, what is the actual physical force that's giving them their centripetal motion? What is the force that keeps them in a circle? What is the force that keeps them from sliding out in a straight line? So as they're going around like this, they're going in a circle, but if they're what force keeps them in a circle and keeps them from just...
Is it the wall or the normal force that they're...
That's exactly right. It's the contact force or the normal force between them and the ditch. And so if they rotate too high on the ditch, they will effectively jump the ditch, and that's where the accident happens. So we're assuming that they stay in contact with the surface of the track. And that provides a normal force pushing them towards the center of the circle.
Isn't there some friction from the blades digging into the ice as well?
There is, but that's going to be mostly forward, and I assume that it would keep them from sliding upwards. But if they were to come outside of the track, like if that groove wasn't there, do you think the blades would keep them in a circular path?
It should.
You're saying if they were to get rid of the ditch and just let them navigate with the blades like skis?
Oh, no, sorry.
Yeah, I'm saying I can see what you're saying. At slow speeds, that would probably work. And that's how skiing works, right? That you're actually using the metal edges of your skis to control your direction. I think at the speeds that they're dealing with and the icy conditions, that it would be virtually impossible for them to make turns like this just using the blades of their
yeah, it would, because those blades can't turn and grip. So, I mean, yeah, the bank curve is obviously a necessary thing. I did speed skating for 6 years, so that's why I was just thinking of the concept being the same.
So that's interesting, because on a skating track, you don't have any embankment. So all that turn, you have to lean hard into the turns.
You do, yeah.
And that's where a lot of the accidents happen, is people lose control going around turns too quickly. Mm-hmm. Because they don't have the benefit of the bobsled.
They don't, and if the ice gets dry, it breaks off, and they lose all their traction, and it's a bad deal.
Yep, and so you see that. That's why those. First of all, accelerating is hard, and so that's a big deal. But controlling those turns in ice skating is extremely hard, and so that's a very demanding sport. Okay, back to this. Yeah, I'm going to say it's contact force, it's normal force. And if you were to rotate too high over the ditch, then you would no longer be going in a turn. You would be going in a straight line and out of control. So what is the centripetal acceleration for each of these turns? How would I find AR for the first turn? This is actually really easy. I'm going to call it AR1. You're literally just plugging numbers into an equation, aren't you? It's going to be equal to V squared over R1 where v is equal to 34 meters per second and r1 is 33 meters, that gives me an acceleration of 35 meters per second squared. Now, we often have a hard time putting those types of numbers into context, and so it is common to divide this number by g and then say you're being accelerated at some multiple of g. Right? So if I were to take this 35 meters per second squared and divide it by 9.8, that could also be represented as 3.6 times g, where g is the acceleration of gravity. Now that gives us something that we can relate to. It means that as they're going through this turn, that their effective weight will be 4 times greater than it normally, well, 3.5 times greater than it normally would be. Or in fighter planes, when you see some of those movies with jet planes, they say that they're pulling a turn of 3 Gs. It means that the acceleration they're experiencing during that turn is 3 times the acceleration of gravity. And in this case, they would be pulling a turn of about 3.6 G. And that's something that we can usually relate to better. And that means that, and that's physiologically very difficult because it messes up the way that blood circulates in your body, among other things. Now, they're only doing it for a short period of time, so it's not like this is an extended force acting over minutes. This is acting over a fraction of a second. But during that fraction of a second, it is possible to black out because your blood is working against that acceleration, and you might, under extreme conditions, lose some of the blood flow for just a moment. And that's why they wear pressure suits, at least in the jet planes. And I assume for the athletes as well, because they're going through these high-speed turns, they need some assistance with circulation. Okay, let's look at the second one. Do you expect it to be greater acceleration or less acceleration for the second turn?
Greater acceleration?
Greater acceleration. Even though they're going at the same speed, they're taking a tighter turn. And you probably know this as well from driving, that the acceleration you experience going around a sharp turn is greater than the acceleration if you're taking a wide turn. Right? And that's what we're dealing with here. So that's going to be equal to v squared over r. And that's going to be equal to, let's see, again, 34 squared divided by 24 is, I get 48 meters per second squared. And that's going to be equal to 4.9 G. Not grams, but gravity. It means that the force they're experiencing as they go through this turn is the equivalent of about 5 times their normal body weight. Which is quite extreme. Okay. So that's everything for today. Since we have just a few minutes left, how are you guys doing on the Chapter 7 homework? Are you finding that homework is probably a little bit more difficult than some of the earlier ones? Okay. Would it be helpful if I had office hours this afternoon? I discussed this with my dean. I have permission to come on campus if I need to. If I held a 1-hour homework session this afternoon on campus, let's say at 3 o'clock, how many of you would be interesting or even able to attend that for the purposes of discussing Chapter 7 homework?
I would be interested, but I can't because I have to pick up my kids.
What time would work better?
Like 10:30.
No, I do the same thing I just did with you guys. I do Act 2 from 10 to noon, so it would have to be in the afternoon.
Yeah, I know. No, it's not going to work for me then.
Okay.
I would appreciate it, but no.
For any of the rest of you, and you know, I could do this virtually as well. I could set up an extra WebEx session this afternoon and just have it open for questions.
After 4:30 would work for me too. What Nate put in the comment section. I don't know if that's getting too late.
4:30 on campus, I think I can do that. I'll have to talk to the secretary and make sure that that's available, but I assume that would work. So let me rephrase the question. If I scheduled a classroom for 4:30 this afternoon, at least 2 people would be interested in showing up, and I can probably record the session as well, or have it online.
Yeah, or I think virtual for me would be fine too if that's easier. Don't know what other people think in terms of virtual versus in person.
Okay.
I could do virtual then as well. I could put a show on for my kids.
Okay.
Yeah, I could do virtual. It's not as much that there are specific questions on the homework I didn't understand, but I'd just like to cover more questions like that if we could. Just more practice.
Okay. That is possible. I'll leave it open as just like office hours. So let's plan on that. I'm going to see what my other class is interested in. And we might just try this physically and see if people show up, and if not, do it virtually. But if I do it physically, I'll try to make sure that it's available in some virtual form as well.
Where would it be if you did it physically?
It would be, I don't know the classroom, but it would be in the Science and Industry building.
Okay.
Probably on the second floor, but I just wanted to know if there was interest. And the reason I asked that is because I'm going to admit to you, I've done all the homeworks. This homework for Chapter 7 is harder than any of the other assignments you've done already. And I don't know if you agree with that assessment, but I think so.
Mm-hmm.
So I expect that people will need more help. Okay, I'll email the class and let you know, but let's plan on having a in-person session at 4:30 for those who are interested, and I will email details, but I will also bring my laptop so that we can try to record whatever gets discussed and take into account virtual participants as well. And if this doesn't work, then we'll try something different next week. Okay? I mean, if this were a regular semester, I would actually be in my office right now, or I'd be in a classroom, and then I'd go to my office and a bunch of you would show up after class and ask questions, and I kind of miss that. So anyway, we'll see you guys either this afternoon or on Wednesday. And one more thing, yes, if you're doing corrections, just email them to me. Try to do it as a single file rather than a bunch of JPEGs. And I will look through those and give extra credit and hopefully have that done before Wednesday. Okay?
Thank you.
All right, we'll see you guys later.